Hi everyone, we're going to talk about Taylor polynomials and using your calculator to calculate Taylor polynomials to approximate a function at a given point or a value for x, and be able to create that polynomial and see what the error is and all of that stuff. So I have one here on the board, Taylor polynomials on the calculator. Following, find the Maclaurin polynomial of degree n given function and evaluate x equals 0.1. Well, the function that I have picked out for our first example here is f of x equals e to the negative x. And the problem wants us to find a Taylor polynomial of degree 5. Okay? So on the TI-89 calculator, to find a Taylor polynomial for e to the x, I'm going to turn my calculator on, clear my home screen here so we can start from scratch. The first step is to get to the Taylor command on the 89, and to do that you're going to press F3, and instead of going down or up, I go down, I go up, because the command for the Taylor polynomial is number 9. I think it's easier to get to if you scroll up. So let's press that. There it is. It's the Taylor polynomial command, and our function is what we put in here first, which would be e to the x. I'm going to put in e to the x. And then we have to tell the calculator what the variable is, and I'm going to say comma x, because sometimes you could have a Taylor polynomial as a function of time, or the function of t, or some other variable. So we have to define what the variable is, and then we have to tell it what degree polynomial you'd like. Well, in this case, we want degree 5, so I'm going to type in 5. And by default, the Taylor polynomial command gives you a Maclaurin polynomial, or a Taylor polynomial that's centered at x equals 0. And so it's as easy as that. You can close your parentheses and press enter, and there is your Taylor polynomial of degree 5 for e to the x. So I'm going to write that down. Here we go. So we can say that e to the x is approximately the Taylor polynomial evaluated, fifth degree Taylor polynomial. Now I'm using an approximation here because we're approximating e to the x with this polynomial of degree 5, and I'm using an equals here because that's what my polynomial is going to equal. So let's put it in increasing order of degree. So this is going to be 1 plus x, if you look at the calculator, plus x squared over 2, plus x cubed over 6, plus x to the 4th over 24, plus x to the 5th over 120. Now, our evaluate the Taylor polynomial at 1 as an estimation for e to the 0.1. So here we go. We're going to say e to the 0.1 is approximately the Taylor polynomial evaluated at 0.1. And that's going to equal 1 plus 0.1 plus 0.1 quantity squared over 2, which happens to be 2 factorial, plus 0.1 to the 3rd over 3 factorial, which is 6. I was going to put the factorial button here. Plus 0.1 to the 4th over 24. I'm running out of space here. Plus 0.1 to the 5th over 120. And that's what I would write down is what my approximation is going to be. And then we can say e to the 0.1 is approximately, using our Taylor polynomial. We can go using the TI-89, using the such that bar, which happens to be right here, such that x equals 0.1. And we are going to get a number, and that's going to be 1.10517. And I have, more digits than the AP Calculus people need, but we're going to use this to see what the error could be. Well, the actual error is going to be e to the 0.1 minus t, the Taylor polynomial of 0.1 of degree 5. This is going to be the actual error, the magnitude of the error anyway. All right, so let's see what that's going to be. I'm going to clear this out. So we can say absolute value of e to the 0.1 minus our Taylor polynomial evaluated at 0.1. Let's just put this in. Close that such that x equals 0.1 and see what our error is. Nope, I don't like that. Oh, you know what I didn't do? I didn't put parentheses around my polynomial. Apologize for that. There we go. I like that much better. It helps when I actually follow my own algebra techniques better by putting parentheses around my polynomial. So this tells me that the actual error is going to be on the magnitude of 1.4089 times 10 to the negative 9. Now that's amazingly accurate, because if you want to see what e to the 0.1 is, that's going to give us 1.105.17. Well, gosh, look at this is the exact value, and that's the approximation. Of course, there are more digits here that we don't see on the screen. If I were to change my digits to not float 6, I could change them to 10 and do this again. Oops. And we'll see a whole lot more digits here. And then let's see the e to the 0.1 here and see more digits. And you see that we're pretty close to exact until we get to this last digit here, which is pretty phenomenal, only using a 5th degree Taylor polynomial. So anyway, so let's review really quickly how we input our calculator to have our calculator to have our calculator create a Taylor polynomial for us. You go to the F3 menu, and then you scroll up to number 9, and then you put your function, which is diamond e to the x, comma x. You got to tell it what the variable is and what degree you want. We wanted 5, and I'm going to close it. There you go. There's your Taylor polynomial, and then you can tell it, you know, I'd like to use that Taylor polynomial to approximate the value of e to the 0.1, so I want x to equal 0.1, and there it is. So I didn't use the such that bar. That would help. It's been a long day. There we go. So there, a quick review on how to do Taylor polynomials on your calculator. Now, I have another example here where we are going to use our calculator to find the Taylor 5th degree polynomial again for f of x equals 1 over 1 minus x. And I want to approximate that using a Taylor polynomial degree 5. And again, I'm using the approximate here because that's going to approximate our function. It's not going to be exact. And the Taylor 5th degree Taylor polynomial is going to be equal to an actual polynomial. So how do we do that on the calculator? Okay, we're going to clear this out. We're going to hit F3, scroll up to our Taylor polynomial command, and we're going to type in our function here, which is 1 over 1 minus x. So 1 divided by, parentheses, 1 minus x, comma, x, comma, we want a 5th degree. So I'm going to close it, and the calculator will compute a 5th degree. Now, this is a pretty simple one because we know what the series is for 1 over 1 minus x. And here we go. So this is 1 plus x squared plus x to the 3rd plus x to the 4th plus x to the 5th. This is the geometric series where the r is x. Okay, and I want to use this Taylor polynomial here to approximate the value of my function here at 0.1. So I want 1 over 1 minus 0.1 to be approximated by the Taylor polynomial, 5th degree. And let's plug it in. So we say 1 plus 0.1 plus 0.1 squared plus 0.1 to the 3rd plus 0.1 to the 4th plus 0.1 to the 5th. And then let's put that on our calculator. Now, how are we going to do that? We're going to use the such that bar. I promise to hit it this time. X equals 0.1. And we're going to get 1.11111. That's our approximation using the 5th degree polynomial. So what is the exact? Well, what happens is that I'm going to put in 1 divided by 1 minus x such that x equals 0.1. And we get 1 with a bunch of 1s in it. So this is a very good approximation for 1 over 1 minus x evaluated at 0.1. And if I wanted to know what the error was, using my 5th degree, the actual error, the magnitude of the error, I would say 1 over 1 minus 0.1. Actually, I'm going to use this just an x. Minus my Taylor polynomial, such that, right, we're going to let x equal 0.1. Let's see if we can type that in the calculator this time. So I'm going to say absolute value (1 divided by parentheses 1 minus x) minus, I'm going to use parentheses this time. I'm going to go up and grab my Taylor polynomial, 5th degree, close parentheses, close the absolute value, and say such that x equals 0.1. And there you go. There is our error, which is pretty small. Pretty good approximation, I think, for 0.1 because it's close to the center. 0.1 is very close to the center of 0. The further you get away from the center, this polynomial is not going to be as good of approximation. So that's how you do it when you want it centered at 0 for the Maclaurin function, which is the polynomial, which is the specific case of the Taylor polynomial centered at 0. All right, so let's go to the next one. This one is going to be following the Taylor polynomial of degree n, given function centered at c. Now, we're going to use a 4th degree Taylor polynomial for 1 over x and have this one centered at x equals 1. Okay, so here we go. So we're going to clear this out. And we're going to get the Taylor polynomial command by hitting F3, going up to the Taylor command. Here's the Taylor command. My function is 1 divided by x. I type that in, comma x, which gives me the variable with which we are going to be differentiating it. We're going to be using as part what our function is defined as a function of x. And then comma, I'm going to make this a 4th degree Taylor polynomial, comma, and now I'm putting a center of 1. Remember, I said the Taylor polynomial command defaults to a center of 0. So if you don't put any center, it will give you the Maclaurin polynomial. So there we go. We're going to have it centered at 1. And here we go. I'm going to hit the magic button, and we get a 4th degree Taylor polynomial centered at x equals 1. And you know it's centered at x equals 1 because it's showing you the horizontal shift here. So let's hop up and let's put it in a nice order here. So I can say the 4th degree Taylor polynomial is equal to, what is that, 1 minus x minus 1 to the 1st plus x minus 1 to the 2nd minus, I go back here, minus x minus 1 to the 3rd plus x minus 1 to the fourth, if I go back even further. Okay, and that's going to approximate 1 over x, centered at x equals 1. Okay? Now, let's say I wanted to approximate 1 over x at a point or a location that was close to 1. Let's say we want to evaluate the fourth degree Taylor polynomial. I don't know, let's get a little bit further away than 0.1. Let's go to 1.2. I want x to be 1.2. Okay, now that's not close to 0, it's close to 1, which is our center, which is what we want. Okay, so we're going to say 1 over 1.12 is approximately 1 minus 1.2 minus 1 plus 1.2 minus 1 to the second minus 1.2 minus 1 to the third plus 1.2 minus 1 to the fourth. And let's see where our calculator tells us. Okay, so I'm going to take this Taylor polynomial and evaluate it at x equals 1.2 because that's close to our center. And we get approximately 0.8336. All right, and now let's see what 1 divided by 1.2 is. So this is the Taylor polynomial evaluated at 1.2, and this is our function evaluated at 1.2, so we're approximating. And this side here is going to equal, or is approximated by 8.3 repeating. That's pretty close. It's not as close as our approximation up here because we were closer to the center. I just decided to show you guys that you could be a little bit further from the center if you wanted to be. All right. So let's do another one. Okay, this function's a little bit more complicated. And this one says, let's create a third degree Taylor polynomial centered at pi. Let me change my piece of paper here. Okay, so here we go. We're going to have our f of x equal x cosine x. And we're going to say x cosine x can be approximated by a third degree Taylor polynomial. And let's see what that third degree Taylor polynomial is. So we can say F3, going up to our Taylor polynomial command, and then it's going to be x times, you have to use the times when you have functions of x multiplied by each other, times cosine x, comma, x, comma, I want a third degree, so I'm going to press 3, comma, and where's the center? Well, the center this time is at pi. So there we go, we got our center at pi, and I'm going to press enter, and the calculator is going to give me a third degree Taylor polynomial centered at pi, and so there we have it. So it's going to start off at negative pi minus x minus pi plus pi over 2 times x minus pi quantity squared. And let's go up here and see the last term. Plus x minus pi cubed over 3. Now let's see if we got that right. Now x minus pi cubed over 2 plus pi over 2 times x minus pi squared. There we go. And there's our Taylor polynomial, third degree, because the highest degree is 3. So this is centered at x equals pi. Now, what would really be cool is if I were to take this polynomial here, and I'm going to copy it using the diamond copy key, and go to y equals here, clear this out, and diamond paste. And there's my Taylor polynomial for x cosine x. And then I'm going to actually type in y2, x times second cosine x. And so this is the third degree Taylor polynomial that's approximating this function. And we're centered at pi, so I'm going to change my window, diamond window. So let's change our window. If we're centered at pi, how about we go from 0 to 2 pi, just to look at the window. And since x cosine x is, cosine x is going to be sandwiched between x and negative x. So I think my window, I'm just going to do negative 10 to 10 just to see, oops, I'm sorry, to see what it looks like. And then we'll adjust our window if we need to. All right, diamond graph. So there we go. The first one it's graphing is the Taylor polynomial, because I don't have them graphing at the same time. There's a Taylor polynomial. And there is the actual function. And actually, I'm going to go back to y equals. And I'm going to make this one a different style. Whoop, that's going to be F6. Change the style. And I'm going to make it thicker so we can actually see the original function. All right, so this is the Taylor polynomial, third degree, that it's graphing out. And remember, I set my window from 0 to 2 pi so that we could see the center. Okay, there you go. Now, at x equals pi, let's do a second, or F5, calculate the value of the function when we're at pi. So I did that so you could see where the center was. And you can see, we're zoomed in pretty closely here, that the Taylor polynomial of degree 3 is a very good model for, this is the Taylor polynomial here. Great model for x times cosine x, very close to pi. Okay, so that's why we're doing this. And I'm going to do a quick question on error, because that's always a popular subject. Error. I hear moans and groans in the background. All right, so the next problem we're going to do is determine the degree of the Maclaurin polynomial that should be used to approximate the square root of e to 3 decimal places by using the Lagrange remainder. Use this Maclaurin polynomial to approximate the square root of e to 3 decimal places. Okay, well, we know that e to the x is equal to 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial plus x to the fifth over 5 factorial plus ... And this converges for all real numbers if we use an infinite number of terms. But they're saying, let's figure out how many we can use to be accurate to a decimal point of 3 places. Okay, so 3 places. Second, quit out of here, and I'm going to go home and clear this out. And so second square root of e to the first here. And if I do that, I get a value of, so e to the 1/2, or the square root of e on the calculator is 1.648721271. Let's see, 1.648721271. Okay, so we want to get at least these first 3 digits here to match using our Taylor polynomial. I mean our Maclaurin series. So we're going to create a Taylor polynomial. So I've got, I'm going to guess. We'll see what happens if I use a degree 3 Taylor polynomial, which would be the first 4 terms up to the 3rd degree here. So 1 plus x squared over 2 factorial plus x to the 3rd over 3 factorial. Okay? And the square root of e is equal to e to the 1/2. So I'm actually substituting in 1/2 here for x. And I'm centered here at 0. Okay, so I'm this is kind of my interval here from 0 to 1/2, because if I'm centered here, this is going to be the best place to be a perfect fit, because the tangent line and all of the tangent properties, the tangent line, the tangent quartic, quadratic, cubic, quartic, quintic, will all share this point. So this is going to be the best approximation. But this one here is away from the center, so it's not going to be as good. So let's see what happens if we do the Taylor polynomial, degree 3 of 1/2. So this is how I would do this on the calculator. I would clear this out, go to the Taylor polynomial command, type in diamond e to the x, comma x, comma, I'm going to use degree 3 because degree 3 is what we're after. And it's centered at 0, so I don't have to show a new center here because it defaults to 0. And I'm going to press enter. So there's my Taylor polynomial. And you'll see that that's the one we have written down here. Now, I'm going to go at the end here and say such that x equals 1 divided by 2. When I do that, I get a fraction, of course. So here we're going to find a decimal. And what do we get? We get 1.6. Oops, sorry. Let's write that better. 1.6458. 3 repeating. Okay, now, is that what we want? Are the first 3 digits here matching after the decimal point, the 1.648? No, not quite. So we still got some error in that calculation. So let's try the 4th degree polynomial. So that's going to be 1 plus x squared over 2 factorial plus x to the 3rd over 3 factorial plus x to the 4th over 4 factorial. Oops, I want to make this an x. I haven't plugged in 1/2 yet. So if I want the 4th degree Taylor polynomial at 1/2, I'm going to do the same command now. I'm going to show you what the 4th degree looks like here. We can press enter, and then that's our 4th degree Taylor polynomial, which matches what we have here. And then I'm going to go such that, oops, forgot the such that bar, such that x equals 1 divided by 2. It is a fraction. And what do we get here? We get 1.648475. Now, there we have it. So we only have to go to the 4th degree Taylor polynomial in order to get the accuracy that this question is asking. But they're talking, the question is actually asking partly about using the Lagrange remainder. So if I were to use a 5th degree Taylor polynomial, this would only get better. Okay, so the Lagrange form of the error is going to be approximated by, let's say, if I use the 4th degree Taylor polynomial as my guide, the next term would be the 5th degree Taylor polynomial. So I'm going to say e to the 1/2 minus t, the Taylor polynomial of 1/2 is going to be less than or bounded by the fifth degree, because that's the next bumped up derivative here, evaluated at some c times the magnitude of our point x minus our center. Our center is 0 here. Oops, make that absolute value bars. Raised to the 5th, because that's 1 degree higher, all over 5 factorial. Okay, now I'm going to make this right here is the maximum the maximum of the fifth degree, of the fifth derivative of your original function. Well, what is our original function? Well, it's of e to the x over the interval from the distance from our center. Now, if we know e to the x, we know all the derivatives of e to the x, don't we? Well, I hope so, because the e to the x is the greatest function in the universe, because you can differentiate it a million times and it'll still be itself. So if I were to graph e to the x here, and I zoned in on the interval 0 to 1/2, the fifth derivative is going to have its maximum at the endpoint over here, which would be at 1/2. So I would say that this error would be e to the 1/2, because that's where it's going to be the worst case, times, and that's a positive number, times 1/2 to the fifth over 5 factorial. Now, let's see if our error actually works. Okay, so we're going to say e to the 1 divided by 2 times 1 divided by 2 raised to the fifth divided by 5. Okay, and you get the factorial button by hitting diamond divide, and that's going to give us a decimal here. What do we get? We get 0.0004293545. Okay, now this is an upper bound of the error if I were to use only the fourth degree Taylor polynomial. Now, how do I know if that's true? Well, I can actually find the error here using the fourth degree Taylor polynomial by calculating what this is the actual error. Because I'm taking the original e to the 1/2 and I'm subtracting its approximator, which would be the fourth degree Taylor polynomial. Okay, so let's do that. I can say absolute value, of e to the 1 divided by 2 minus my Taylor polynomial of degree 4. I'm going to hop up and grab my Taylor polynomial of degree 4. There it is. And I put my parentheses around this time again to save myself some misery. All right. And I'm going to go such that x equals 1 divided by 2. Press the magic. Oops. I don't want the exact. I want the approximate. So that's the actual error. So what does the actual error say? Its actual error is 0.002837707. Wow. I'm not sure I like that answer. I used e to the 1/2 here. Let's see if I did my calculation right. Use my fourth degree Taylor polynomial. E to the 1/2. That's going to be the maximum over the interval from 0 to 1/2 of the fifth derivative. And I'm going to be 1/2 away from my center, raised to the fifth over 5 factorial. Interesting. Let's see, what happens if I subtract these two numbers? 1.648437 minus 1.648721,271. Okay, well, so why is my Taylor polynomial not doing this right? Let's see, let's try another calculation. So this one is no, I left a 0 off. You know what? I sat there and was worried that, oh my gosh, how am I going to explain this because it's not right? And guess what I did? I left one of the leading zeros off. So I can joyfully say that this is an upper bound because this is smaller. So there you go. So it helps when I read my calculator right and show that I have 3 zeros in front. I feel much better now. Much, much better. So this is definitely an upper bound because this number is bigger than this number. So this is the worst case scenario for the error. And how did we figure that out? Well, we found the maximum value of the first, the derivative after the derivative that you would use to calculate the 4th degree Taylor polynomial. We found the maximum of that 5th derivative over the interval from the center to the outside edge of your, because if you're approximating at 1/2, you're going to be 1/2 away from your center. So you say 1/2 to the 5th over 5 factorial. And that's going to give you an upper bound using the Lagrange error bound formula. Okay, I feel better. Sorry about that mix up there. It's late in the evening and I'm trying to get this in so you guys have something to study with. Okay, and I'm going to do one more. Well, maybe 2 more. We'll see. All right. And it only took a 4th degree Taylor polynomial to get 3 decimal places of accuracy of e, square root of e, which I think is pretty amazing. All right, so this next one says, let f be a function given by f of x equals cosine 3x minus pi over 10, and p of 4 of x, p sub 4 of x. This is another way you could write Taylor polynomial. Be the 4th degree Taylor polynomial about f at x equals 0, which is another name for the Maclaurin. Okay, so let's figure out what the 4th degree Taylor polynomial is using our handy dandy calculator here. Now, how do we get there? We go F3, scroll up to the Taylor command, and type in our function, which is cosine of 3x minus second pi divided by 10. Close that. My variable is x, comma, and I want the 4th degree Taylor polynomial, and it's centered at 0, so defaults at 0. I don't have to put a comma 0. And I'm going to press enter, and I would like to have no decimals. Okay, so it's a little bit messy, but here it is. And I'm going to put it in the right order. All right, now I have taken the liberty of doing this problem earlier so that I wouldn't know what I was doing when I got on air here. So here we go. This is square root of 2, root 5 plus 5 divided by 4, which is such a pretty number, isn't it? Plus 3 times the quantity root 5 minus 1 over 4 times x minus 9 times the square root of 2 times root 5 plus 5 all over 8 x squared. I'm going to scroll to the next line here. 9 times root 5 minus 1 quantity cubed. I'm sorry, it's x quantity cubed. X cubed over 8 plus 27 square root of 2 times root 5 plus 5 all over 32 x to the 4th. Okay, now we are going to use this Taylor polynomial as an approximation for f of x. But the question's asking us to use the Lagrange error bound to show that the magnitude of the error is less than 1 over 500. Okay, so I'm looking at my Taylor polynomial here. It's degree 4. So the next degree, the term that, or the derivative that we would have thrown away would be the 5th derivative. So I hate these are both the 5th derivatives, but anyway, so we're going to say that the magnitude of the error evaluated at 1/4 minus the Taylor polynomial fourth degree evaluated at 1/4 is going to be less than, well, using Lagrange, we're going to have the magnitude of the fifth derivative evaluated at some c. Remember that this is the maximum. We got to find the fifth derivative and find out what the maximum is over the interval 0 to 1/4, because it's centered at 0, times 1/4 minus 0, which is the center, raised to the fifth, because that's the degree higher, over 5 factorial. Okay, so I need to know, remember that this is the max of the fifth derivative over the interval from 0 to 1/4, which is the distance from my center to where we're approximating it, our function at. Okay, so I need to know what the fifth derivative is. I need to know what the fifth derivative is of f of x. So how do we do that? We're going to go second derivative of cosine of 3x minus second pi divided by 10. Close that, comma x. You got to tell it what the variable is, comma, and I want the fifth derivative. So there we go. I'm plugging it in. There's my fifth derivative. Wow, that's a pretty big leading coefficient. So my fifth derivative of x is equal to 243 cosine of, now the calculator, does some things with the argument here, but it's equivalent. It has 3x plus 2 pi over 5. Okay, and I'm going to have to figure out what the maximum is of this function, this fifth derivative function, over the interval from 0 to 1/4. Okay, so let's graph this function. I'm going to hop up here. Oops, I'm sorry, and copy it with using diamond copy, and then go diamond y equals, and I'm going to get rid of this one and put diamond paste. And there's my function, and I'm going to change my window because this coefficient is so huge, it's 243. I'm going to change my window to go as far as 250 just to see. And I'm going to make my interval very small, like negative 0.5 to 0.5, because I need it at 1/4, which is 0.25. So I think that'll cover us there. All right, and we're going to go diamond graph. And there it is up at 243, and it's coming down. And I need to know what the maximum is between 0 and 1/4. Well, this function is clearly decreasing after 0, past 1/4. And let's see, I'm going to go and expand the window here. Let's make this negative, I don't know, negative 50, just to make sure we get, although 0.25 is right in the middle of this, I need to make it bigger. Let's just say negative 100. All right. Let's see if I get all the way to 0.25 in this graph. I'm close. I'm avoiding making it negative 250 to 250. So here it goes. I'm making it 250 to 250. Just so we see the whole thing, the whole kit and caboodle. Okay. Now, I need the magnitude of the error between 0 and 1/4. So I'm going to go F5, find the value of my function when x is 1/4, which is 0.25. And what is the error here? It is, I'm sorry, what is the value? It's 102 point, is that 588? Okay, so the worst case scenario between 0 and 1/4 is 102.588. Okay, so that's the magnitude of negative 102.588. That's going to be the worst case scenario. So I'm going to put in here 102.588, because that's the maximum of the interval there, times 1/4 to the fifth over 5 factorial. And this is stored in YC. So I'm going to go home, And let's do our calculation. We're going to do negative, y alpha c, because that's where our value is stored, times 1 divided by 4 raised to the 5th divided by 5 factorial, and we get less than 0.0008. I got all, no, I didn't, did I? Let's see, 1, 2, 3. Yes, I got them all. 3, 4, 8, 6, 3. So that's using the fifth derivative to calculate what the Lagrange error bound would be. This is going to be the upper bound on any possible error over the interval from 0 to 1/4. Now, how do I know it's less than 1 over 500? Well, because 1 over 500 is 0.002. And this is definitely less than 0.002. Okay, now I have one last example. If you weren't really sure about what we were doing, one last example. Now here we go. Let f be a function having derivatives of all orders for all real numbers. The first derivatives at x equals 2 are given by the table. The fourth derivative of f satisfies the inequality. The fourth derivative of x is less than or equal to 50 for all x in the interval from 2 to 2.5. Okay, now, what's fascinating about that? Well, they're telling us what the maximum is for the fourth derivative, and they're giving us the first three derivatives, okay? So we want to know what the upper bound of the error is at 2.1. Okay, well, the center is where? The center is at 2, according to this problem. Okay, so we can say, using the Lagrange error bound, that the f of 2.1 minus the Taylor polynomial, and I'm going to use t in this case, Taylor polynomial degree 3, evaluated at 2.1, is going to be less than the maximum of the fourth, right, evaluated somewhere. That's absolute value. We're going to find that. And then the center is going to be 2. So we're going to go 2, whoops, put absolute value bars here. And then absolute value bars here. And then it's going to be 2.1 minus 2, which is the center, raised to the fourth now. Why is it raised to the fourth? Because this is the third degree Taylor polynomial, and we're going to get the very next term that we didn't use, over 4 factorial. And they told us, well, goodness gracious, this is the max of the fourth derivative of f over the interval from 0 to 2.1. And they're telling us that it's less than or equal to 50. So we're going to say 50 here times 0.1 to the fourth over 4 factorial. Now, their interval they gave us from 0 to 2.5, they're telling us the maximum is 50 over that interval. So we're going to be generous and make this the worst case scenario. Okay, now, well, doing that on the calculator, we're going to hit 50 times 0.1, not 0.01, raised to the fourth, divided by 4 diamond factorial. There we go. And we're going to get less than 0.000283. And it says use the Lagrange error bound to explain why f of 2.1 has got to be less than 8.5. Well, this is the error. This is the upper bound of the error. Where is that the upper bound of the error? At 2.1. Okay, so we can say that the error is going to be lower than this. And our function table over there says f of 2 is 8. So f of 2.8, I'm sorry, 2.1, is going to be, it's going to be at least close to 8 by this much. So this is going to be 8.000283 at the worst, which is less than 8.5, which I think is pretty amazing. Okay, so there you have it. All right, well, have a good rest of your night. Thanks.